what do we have here? We have a sphere of radius r capital. Then there is a charge q. Let's assume it's positive charge, uniformly distributed over the whole sphere. Uniform distribution. Of course, yeah, we're just looking at the simplest possible situation. Of course, the distribution of charge can be more complicated, but it's still reasonably simple if you have not uniform distribution, but still spherical symmetry. Even in that case, application of the Gauss's law is reasonably simple. Of course, integration will be more complicated, but the procedure will be pretty much the same, with more complicated integral. But anyway, so here we have uniformly charged dielectric sphere, right? It's not a metal, it's not a piece of metal. Metals will be discussed later, right? Okay, so that's what is given, and what we need to find electric field. We need to find expression for the electric field outside of the sphere and inside. Okay, I will write A. There will be two parts. In the first part, in part A, we will find electric field outside of the sphere, and then in the second part, inside. Right. So let's find electric field, question mark, and I will write outside, where r small is larger or equal r capital. Outside or on the surface. Right? Okay, so, and as I just told you, I want to emphasize that now we have two alternative, equally strong approaches which can be used to find electric field. Either Coulomb's law with the probe charge or Gauss's law. In this case, although we have a nice symmetry, application of the Coulomb's law, right, integration like we did what a couple of classes ago. In this case, it will be significantly more complicated relative to the Gauss's law. But application of the Gauss's law over here, it's just pleasure to use. So we're going to use Gauss's law. So if we want to use Gauss's law, of course, first of all, we need to write it. E dot dA equals to Q enclosed over epsilon naught. Okay. What do we have to do first? Which step do we have to make first? Without that step, we will never be able to move any further. The first step, think for a second, right? Without that step, we will never be able to do anything. Look, integration is done over what? In order to integrate that, we need to know surface, because this is integration over a Gaussian surface. Then also, in order to find Q enclosed, in order to see which charges are enclosed, we need to know a Gaussian surface. So the first step in application of the Gauss's law, we must pick a Gaussian surface. Otherwise, you cannot start taking this integral, because the surface is not, you haven't decided over which surface you want to integrate. And of course, you wouldn't be able to write the value of Q enclosed if you don't know which surface is used. Right. First step, Gaussian surface. Right. Okay, which surface can be used as Gaussian? Okay, let me first write a Gaussian surface. Okay, which surface? First of all, Gaussian surface must be in the region where you want to find the electric field. It makes sense. It's like if you want to sample the life, I know, in Canada, you don't go to Madagascar, right? You go to Canada in order to sample life, the level of life, or so on, right? And the same here. If we want to find electric field outside of the sphere, of course, our Gaussian surface must be outside. And of course, it must be closed. Then, so first, then, of course, you can, as I keep telling you, you can use any closed surface as a Gaussian surface. Virtually any surface your soul desires, right? Or I don't know, heart and kidney desires, right? And you will never be wrong with any surface. For example, let's say you decide to use a surface like this with very complicated shape, right? I will never be able to tell that that is a wrong choice of the surface. Never. Because, yeah, Gauss's law can be applied for any surface. But the thing is, we need to solve this particular problem. We need to find the value of the electric field, expression of the electric field, right? And with your kind of correct surface, you will never be able to complete this problem just from the mathematical point of view. So in this case, the fact that you are correct is useless. You will never be able to solve the problem. So on top of being correct, we must be wise and pick the best possible out of infinite number of possible options for the Gaussian surface. We need to pick the best one so that the amount of mathematical work will be minimum, and so that we can use the symmetry of the problem. Because with a complicated choice of the surface, you will never be able to use the symmetry of the problem, right? So we need to pick the best Gaussian surface. And you should be able even to guess what is the best Gaussian surface, right? It will be the best Gaussian surface is a concentric sphere of radius larger than r capital. Over here, concentric, it means centers of both spheres are the same spot, right? So the best Gaussian surface in this situation is the concentric sphere. And I will justify it when we start going through the solution. I will justify this choice. Right. Okay, so the best Gaussian surface, I will use a green dash line. So that's my Gaussian surface. Okay, let me do it this way. So this is my Gaussian surface. Okay, it's slightly distorted, but it's a concentric, it's a sphere. I didn't graduate from an art school. I graduated from the physics department, so that's why it's slightly asymmetrical. But anyway, and of a some radius r small. Basically, r small, it's sort of like a variable. It's some arbitrary radius r small. And of course, this r small is larger than r capital. Okay, so that's the first step. Now, after this step, we can start actually evaluating the left-hand side and right-hand side. So usually I start taking care of the left-hand side first. Okay, so integral of the closed surface. Okay, closed our Gaussian surface E dot dA equals. Okay, now I will pause because now the most difficult part almost. We need to take this integral, which is again calculus integral from from the calculus 3 course. And of course, you don't know how to take these integrals, but nevertheless, we will still be able to take this integral. Okay, in order to take this integral, let's first draw all these vectors on a picture. Electric field vector, area vector, and so on. And again, you need to remember that in this integral, all the time we are on this Gaussian surface. We're not on that surface of our charged sphere. No, because very often students just draw these vectors on that charged surface. No, we are on the Gaussian surface. We're not allowed to step away from this Gaussian surface. According to this law, we are on the Gaussian surface. Right? Okay, so let me first draw dA. Right, and you remember the convention. The area vector must be perpendicular to the surface and point towards the outside. Towards the outside because of the convention. You remember in the previous class when we were discussing the electric field. So, if for example I take this patch, small patch, right? It's a dA, right? It's basically what? It's a cross section of the sphere, right? So let's say this is my dA. Right? And all right, so of course it must be perpendicular since this is sphere. perpendicular, it means the dA will be radial. Okay, so that's my dA vector and points towards the outside. So, and so of course, since during this integration, we're going to take care of all the patches on this green surface. Oh, let me draw a few other vectors on a few other patches. For example, let me take this one. Here will be dA, right? Over here I can take one. So this is my dA, and so on. Of course, you can draw as many as you want, but usually one or two is enough. Okay, so now we see direction of dA. Now, what about electric field vector? What's the direction of the electric field vector? Usually books say something like this. It's obvious because of the spherical distribution of charge that the electric field will be radial. Basically, radial, it means like this way, right? I usually draw an additional picture to make it clearer, to justify, okay, in my opinion, maybe slightly better, right? Not just with words. Okay, so let me now give you a small justification of a radial direction of the electric field. Okay, let me draw underneath additional picture. All right, so let me write justification of radial E direction. Okay, let me do it this way. Let me redraw this picture smaller. So let's say this is my charged sphere. This charged sphere of radius r capital, right? Okay, let me even show. Maybe this is r. And let's say, for example, I want to find direction of the net electric field at this point. Okay, let me draw auxiliary line which goes through the center of the sphere and through the point where I want to find direction of the electric field. And since this sphere is uniformly charged, so we have charges at every point. So let me take, for example, small piece of charge over here, completely arbitrary point. Just small piece of charge, right? And basically point charge. And of course, we know electric field lines over point charge, right? They're radial, right? And so let me draw contribution from this point charge to the net electric field from this point. Now, at this point, we can do that easily, right? So let me draw dash line. And of course, the electric field will be this way. But at the same time, I can find symmetrically positioned charge, symmetrically relative to this line, position charge over here. Also point charge. Because we have uniform distribution of charge, we can find point charges pretty much anywhere we want. So I decided to look also at this symmetrically position. And now let me draw contribution to the net electric field from this point, from this blue charge. Okay. Okay, of course it will be this way, E. And now let's add these two vectors. Of course, radial components, this radial component, and, oh, not radial, sorry, tangential component, this tangential component of the blue field, and tangential component of the red field, they cancel each other out. And if you add these two vectors, okay, let me use red, all right. And if you add the radial components, of course, they will give us this net electric field, all right, pure radial. So pretty much for any charge over here, I can find symmetrically positioned charge, and their tangential components are going to brutally cancel each other, leaving only radial components. So pretty much it doesn't matter which point I take, here, 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 or anywhere around the charge sphere, electric field is going to be radial. All right. So pretty much that's why usually books usually say, right, because of the spherical symmetry, the electric field is going to have only radial direction, right? So I can draw basically here, 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 electric field lines, right? But I'm not going to draw those lines. I'm going to draw just electric field vectors next to these dAs. Okay, so let me draw here, E, here, E, and maybe here, electric field. Okay, so now I see pretty much almost everything about the electric field. Okay, I see directions. Let me see. I see directions of E and dA. So now I will open my explanation box and write so E, or I can say since E is parallel to dA, right, you see, the same directions, I can simplify this dot product or scalar product. So I can write E dot dA equals to E dA n times cosine of angle. I'm just writing explicitly dot product of two vectors, EDA. Okay, let me just finish this line and then we'll have a break. So absolute value of E, absolute value of dA, and then cosine of angle between these two vectors. What is the angle between these two vectors? These two parallel vectors, the angle between them is 0 degrees. 0 degrees. So as a result, I can write this cosine of 0 degrees is 1, so it will be just E dA. Let me close my explanation box and let me continue over here. So now instead of this integral, I can write integral of E times dA. What's the major achievement over here? Here we have products of vectors. This is vector, that is vector. Now after this first step, now it's the magnitude of E and magnitude of dA. So now we have just a product of two magnitudes. They are no longer vectors. There's a scalar function. No vectors. So that's the achievement of the first step. So now next step, in order to take this integral, now this is the absolute value of E. Let's imagine you sit over here on this patch. Imagine yourself sitting on this patch on the Gaussian surface, right? This electric field, and here we have magnitude of that electric field, right? This electric field is created by what? By this distribution of charges. So look at those charges, remember, and now let's move yourself to the different point. Let's, for example, move yourself to this point. And look at the distribution of charges from this point. Will it be the same as distribution of charge you saw from this point? Of course, because of the spherical symmetry, distribution of charge, if you look from this point, will be exactly the same. It means what? If your distribution of charge is exactly the same, it means what? It means that electric field strength at this point will be exactly the same as here. Magnitude of the electric field strength, of course, directions are different. Electric field direction over here that way, over here will be this way. But we need to know about the magnitude and the magnitude of the electric field over here, here, or any other point. You can move yourself to this point. Again, distribution of charge will be exactly the same. And of course, electric field magnitude of the electric field strength will be the same. So basically I'm claiming, because of the spherical symmetry, electric field magnitude at any of the points on the Gaussian surface, because again in this integral we are staying on the Gaussian surface, right? Electric field strength is the same, not vector strength. At this point I couldn't say that, because here we had a vector, and vector had different directions. But once we managed to get rid of a vector, now it's a magnitude strength. Now I can use this fact, okay, electric field strength is the same. And if now, so as a result, so this E is constant on the Gaussian surface, right? And what can be done with a constant inside of the integral? Constant factor, right? we can take it outside. We can extract it. You remember I told you about the problem with the Gauss's law. Major problem, it's difficult to extract electric field from the sign of integration. But in this case, because we have a nice spherical distribution, extraction is trivial. So now we can extract this electric field, and this is the most important point. So now, okay, let me again open my explanation box, and I will write, since electric field is constant, and I will add on the Gaussian surface. Because in this integral, we stay on the Gaussian surface. Sometimes I see students write, because electric field is uniform. No, no, no. Uniform electric field, you remember, it's exactly the same at any point in space in the same direction. But here, directions are obviously different, right? And about the strength, if you, for example, step away from the Gaussian surface, move closer, electric field goes up. Strength, electric field strength. If you move farther away from the Gaussian surface, of course, electric field becomes weaker, right? So you see, electric field is not uniform. Here, electric field just a constant on the Gaussian surface. Basically, we use the symmetry. We utilize the property. Use the symmetry of the problem. Okay, so since electric field is constant, we can extract it. As a result, we are getting that E integral over the closed surface dA. And now you can tell me what's the value of this integral. Okay, if electric field is constant, whatever situation is, if electric field is constant on your surface, then you can extract it out of the sign of integration. But in this case, yes, because we picked the best possible surface. If you pick, instead of sphere, ellipsoid, which is absolutely correct, nothing wrong with using ellipsoid over here. But in that case, if you have an ellipsoid, okay, let me draw another picture. If you have an ellipsoid, so let's say this is your charged surface, all right, plus, 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 and let's say you pick an ellipsoid. This is your Gaussian surface. Look, over here, electric field will be obviously stronger than electric field at that point, right?
Yeah.
Because this point is farther away. So in this case, if you pick this surface, this ellipsoid, again, I would never be able to tell you that, no, you cannot use the surface, you are wrong. No, you will be right, you would be right, but you will never be able to use all the steps. It means that your mathematics will be ridiculously complicated. And I doubt that you would be able to finish this problem and solve it. Again, you will never be wrong, but you will get very low score and points, right? And because you will never be able to solve the problem, you will never be able to achieve the goal, right? A most important step, the first step, right? You need to pick the best possible Gaussian surface. Otherwise, you will never be wrong, but you will spend half of your life, right, solving a simple problem, right, instead of solving it using, I don't know, in 5 minutes.
Mm-hmm.
Right? And plus, even in this case, the first step, you would never be able to complete the first step. Because, electric field will be still radial, right? Because we cannot change with our imaginary Gaussian surface, we cannot change direction of the electric field. It's a wishful thinking, right? If with our imagination we can change direction. No, electric field will be still radial, right? So electric field, will be still like that, right? But what about the area vector in this case? For this ellipsoid, area vector over here, it will be in the same direction as the electric field, right? So let's say this is dA. But over here, dA will be that way. Over here, dA will be that way. So you see, dA and the electric field are no longer parallel. They will be parallel only in a couple of spots, maybe in a few spots, right? As a result, we wouldn't be able to use this step. We wouldn't be able to use this step, right? So, but since we pick concentric sphere, this is possible. This is correct. This is correct. But even with the ellipsoid, it's already becomes significantly more complicated. What's the value of this integral? What's the answer? Okay, again, I keep keep telling you this. I keep telling you the same thing. Strictly speaking, from the mathematical point of view, this is still not it's not a trivial integral. It's still calculus 3. And at some point you will learn how to handle this integral, right? But we know the meaning of this integral because electric field now is outside, and what we have integrating over the closed surface over our Gaussian surface dA. Since now we should be able to, we understand the meaning of this integral, we should be able to tell the answer. Again, what is dA? It's the area of the small patch, of a small patch on the Gaussian surface. So, and again, what's the meaning of an integration? Integration is just a fancy word for adding small things, small contributions. In this case, small contributions to the total value of the integral, right? So, small value of dA, small area, plus next patch, again, area of this small patch, plus area of this small patch, plus, and you keep adding small areas of all these patches. And when you complete the whole surface of the Gaussian surface, what are you going to get? The total surface of your Gaussian surface. No, it doesn't sound right. The total area of the Gaussian surface, right? The total area. And of course, we know the radius of our Gaussian surface. Its radius r small. So what's the answer? We all know from high school, the area of a sphere. 4 pi r squared. Okay, let me write that down. So this will be equal to 4 pi, and again, careful, r small squared, because lots of students just pick whatever radius is they see r capital. No. We are on the Gaussian surface in this integral, so it's the area of the Gaussian surface. So we need to use radius of the Gaussian surface, r small. 4 pi r squared. We managed basically to take the integral without actually taking it, because we've made first two preliminary steps, extracted electric field, and now it's just the area of the sphere. So it's equal to E times 4 pi r squared. So what we just found, it's the value of the electric flux. It's the value of the electric flux through this closed Gaussian surface. It's a number of electric field lines crossing this Gaussian surface. That's what we found. That's the electric flux, right? And yeah, again, back to the extraction. Look, usually I call this first step in the extraction of the electric field. It's sort of like a preparation for the extraction. We managed to get rid of vectors, and now it's just the absolute values. And then the second step is the actual extraction. It's like in a dental office. Before they extract the tooth, first they use anesthesia, right? So this is like anesthesia, and then the actual extraction of the truth, extraction of the electric field, right? Okay, so that's the value of the electric flux. And now back to our Gauss's law. And according to the Gauss's law, it must be equal to Q enclosed divided by epsilon naught. Equals to Q enclosed divided by epsilon naught. So that's now what we have. So what do you need to do? Somehow using some other reasonings, you need to find Q enclosed, and then once you know Q enclosed, you can solve it for E, the final goal. But now we need to somehow find Q enclosed using the meaning of Q enclosed. So now let me write Q enclosed. The meaning, you remember, it's the total charge within inside the Gaussian surface. So at this point, by looking at the picture, all of you should be able to tell me what's the value of Q enclosed. Again, it's the total charge physically embraced by your Gaussian surface. And again, you remember, where those charges are doesn't matter. Gauss's law doesn't care. You remember we discussed properties of the Gauss's law. Distribution of charges doesn't matter as long as that charge is inside of the Gaussian surface. our Gaussian surface over here. So the total charge sphere is inside. Do we know the total charge inside of that charge sphere? Yeah, it's given. It's Q. And it's all within the Gaussian surface. So Q enclosed is total charge Q. In this case, it's trivial. So Q enclosed, in this case, Q. And again, guys, sometimes I see students write the final answer, because after this we can just solve immediately for E. They write the answer in terms of they just write Q enclosed. No. Q enclosed shouldn't be in your final answer. What should be in your final answer? Q without any subscript and R. The final answer must be written in terms of what is given and the variable. In this case, variable is R small, right? Because we're going to get electric field as the function of R. Right. Okay, so now Q enclosed in this case is trivial, is just Q. Okay, so now basically we're almost done. Let me just rewrite it in terms of Q. So it will be E times 4 pi R squared equals to Q divided by epsilon naught. So now that can be solved finally. And that will be our final expression. Now I will write it E as the function of R. Right. E as a function of R. So it will be Q over 4 pi epsilon naught and R squared. So, and of course that is for R small, larger or equal, R capital. That's for the outside. So let's frame it. Of course, we almost spent like half an hour solving this, although strictly speaking it can be done in 2 minutes. Right. But of course, every time I'm trying to justify every step, explain every step, right? So I'm trying to be as thorough as possible. Okay, so that's the part A. Now let's do part B. Let's find the electric field inside. So now I use blue. So now basically part A and now part B. Right, so part B, we need to find still electric field, but now it is inside for R small, smaller or equal to R capital. So now I'm thinking, you know what, I will recycle the same picture. Again, we will use Gauss's law. Gauss's law, right? Again, it will be integral of the closed surface E dot dA equals to Q enclosed over epsilon. And again, which Gaussian surface we're going to use, right? Again, without that step, we wouldn't be able to move any further. And again, since now we're interested in the electric field inside of the sphere, our Gaussian surface must be inside. I think now I don't have to justify that the best Gaussian surface will be another sphere, but now inside. Again, sphere, concentric, Gaussian sphere will be concentric with our charge sphere, but now it will be inside of our charge sphere. Okay, so now let me draw. You know what? I can probably use. Yeah, I have a bunch of plates which I used to draw pictures. This is container. It's a takeout container. I think it was from one Indian restaurant, I think. So I use them. Okay, so this will be. This will be my Gaussian surface now. Right. And again, of some arbitrary radius R small. But of course, now R small is smaller than R capital. And all right, so this is also Gaussian surface, right? But for part B, so this is for part B. Now, From this point, once you pick a Gaussian surface, okay, let me write again, Gaussian surface. The rest of the steps, these steps, up to this point, will be exactly the same. Not a single symbol is going to be different. So over here, you can just rewrite all this up to this point. Of course, I'm not going to do it. And of course, now dA will be over here. Let me draw a few dAs, right? So let's say this is my dA, right? But now, of course, it will be on this Gaussian surface. Electric field will be still radial. So this will be electric field and dA for part B. So all these steps up to this point are going to be exactly the same. So I will write in exactly the same way. Okay, after exactly the same steps, after exactly the same steps, we'll get, I will just write this part which is underlined, exactly the same. So it will be E times 4 pi r squared equals to Q enclosed over epsilon naught. And now, basically, again, we just calculated the electric flux in terms of, as a function of R. And now we just need to take care of Q enclosed. So the next step, what about Q enclosed? So now, Q enclosed in this case. So first of all, we need to see on the picture, where is this Q enclosed? Again, it's the charge, total charge, within your chosen Gaussian surface. Now your Gaussian surface is here. So the charge which we want to find is this. Let me highlight it sort of like this, right? So this is where our Q enclosed. Again, that's for part B, for this part B. You see? Again, it's just the total charge physically embraced by Gaussian surface. This is our Gaussian surface, so that's the amount of, that's where Q enclosed is, right? I doubt that you disagree with that. Okay, so now, and it's obviously that this Q enclosed is less than Q, is less than this Q which we used in part A. So now we just need to find that smaller amount of charge. We want to find the amount of charge in this volume. So it's not dV. We can easily write the volume of the Gaussian surface. So now I will remove this dV, like what we had in that formula, and we can write we can write the volume of, okay, that's not the good V. All right, so V with the radius r small, and that's our Q enclosed. So volume charge density times the volume of the Gaussian surface, because that's where because inside of that volume our charge Q enclosed. But of course, right now we don't know volume charge density. But can we find volume charge density? We know the total charge Q is uniformly distributed over the whole sphere of radius r capital. That was given from the very beginning. Q divided by the volume of the sphere of radius with radius r capital. Okay, let me write it even explicitly. So it will be Q divided by 4 pi over 3 r capital to the power of 3. Okay, so now let's plug it, and let me write it first in terms of V. So it's a Q divided by V sub r capital and times V sub r small. So just plug it. And we're almost done. So let me write that explicitly. That will be Q divided by 4 pi over 3 R capital, it's this part, and times volume of the Gaussian surface. Wait, R cube. 4 pi over 3 gets cancelled, and we have the answer. Q times R to the power of 3 R small divided by R capital to the power of 3. So that's what I usually do. Some students find the other way of writing it down easier to understand. I remember once I was explaining to one student in my office, and she kind of found, wow, it's easier. Okay, so now I usually start showing two methods. Let me show the other way of finding this Q enclosed. Right. Okay. Okay, let me write. Or it can be done like this. Okay, so let me write volume charge density. Again, by definition, volume charge density is what? You take the charge, total charge, and divided it by the volume over which that charge is distributed. Okay, so first let's use this way of finding rho using the total charge, because we know this total charge is distributed over the sphere with radius r capital. Just typical way of finding. So let me write that first. Q divided by 4 pi over 3 r capital to the power of 3. But how else can rho be found? Also, I can write also rho. Okay, you know what? I don't like this. Or how else rho can be found? Because we have uniform charge distribution. Charge density is exactly the same. Can we write rho in terms of Q enclosed? What if I write rho in terms of Q enclosed? I know that this Q enclosed is uniformly distributed over this sphere with radius r small. Right? So I can take Q enclosed and divide it by the volume over which Q enclosed is distributed. So I can write it also as this. Q in divided by now 4 pi over 3 r small to the power of 3. And this density and that density is the same because we have uniform charge distribution. So now I can, let me remove this or, I can put equal sign. And so now this and that part are going to give us. So from here, I can solve it for Q enclosed. Right. So this goes up here in the numerator. And we will get exactly the same answer. So it will be Q times R to the power of 3 R small times R capital to the power of 3. Some students, when I explain this way, they find it easier to understand. Although, strictly speaking, I still, that is pretty much as simple as that one, this option. Right? So you can use either this or that. Right? Okay, so now, once we found Q enclosed, now it's time to plug it back to what we got from the Gauss's law and complete the problem. Okay, so now let me write so back to our Gauss's law. Or what we got from the Gauss's law, pretty much back to this point. Okay, so let me rewrite it with that expression for Q enclosed. So E times 4 pi r to the power of 2 equals, so it will be Q over epsilon naught and the ratio of these cubes. So r to the power of 2 r's over here and 2 r's over there can be cancelled, right? So this r goes over here, we'll get just 1 1r. And so as a result, the answer will be equal. So now we just need to solve for E. And now I will write E as a function of r. So it will be equal to what? Let me first write all constants. Q divided by 4 pi epsilon naught r to the power of 3. Right. So that's for r small less or equal than r capital. So now let me frame it. That's part B. Yeah, part B is slightly more complicated because you need to spend a little bit more efforts finding Q enclosed. Okay, so the last piece, let me just plot how electric field changes with radius. All right, so what if I plot E versus R? And let's say this is the surface of the charge sphere. So inside, this is some constant. If R and Q, R capital and Q are given, so this will be just some number times variable R. So for R small less than R capital over here, we'll have a linear dependence. We'll have just a straight line. Electric field grows linearly. Right, so let me draw first this dash line. And now proportional to R. And now outside this. Again, Q over 4 pi epsilon naught, this is constant, and the variable is over here. It's a 1 over R squared. So it will be some kind of curve like that. Something like this, decaying as 1 over R squared. So this is over here proportional to R. Over here it's proportional to 1 over R to the power of 2. So that's how electric field changes with R. Our electric field created by a uniformly charged non-conducting sphere, or for now we can say dielectric sphere, because if it were a conductor, the story will be slightly different. We will discuss that in a few minutes.